Alright, so for this lesson we're going to look at modeling with trig. We're going to use some of the functions we've learned and some of the stuff we've seen before to apply it to some sort of real life situation. Here's my form of sine, which we'll call the general formula or the general equation of sine. And here it is written again. This time b is inside the bracket with x and c. This is called your general equation or general form of a sine graph, and it represents any possible sine function that you could get. Right, so we're going to use this version of it here. Now there's a reason for this. Using b outside the brackets, but still within the sine function, allows us to take a shortcut. So we're going to model a real life occurrence or something like that is a periodic event, such as the tides, the seasons, or the wheels on a bus, something that goes up or down or round and round can be modeled by a sine function. So the tides go up and down, or the seasons get warmer, colder. Right, so for this example we're going to model the amount of daylight in a particular day in Auckland. So the longest day in Auckland is approximately 15 hours of daylight. The shortest hours are 10 hours. And the longest day is on the 21st of January. So we're going to try and write a model for this using a sine function. Right, so here's our formula again. We'll begin with y being the daylight, the number of hours of daylight, and x can be the days of the year. And when x is equal to 0, that's the start of the year. So y will be equal to a times sine of b times x plus c in brackets plus d. So that b times x plus c is inside the sine function. Now the first thing we'll look at is the amplitude, then we'll deal with the period. We'll leave c till last because it's probably the trickiest part to understand, and d, which is the vertical shift. So using those four things you can manipulate your graph, and that will give you any possible sine function. Right, looking at the amplitude first, the maximum value is 15, the minimum is 10. So if we draw a graph of that, roughly it's going to look like this. There's some middle point, that's the rest point of the graph. It goes down to 15, it goes up to 15 and down to 10. The distance it goes from rest is the amplitude. So our amplitude is going to be from resting point up to the top of a wave or down to the trough. That's 15 minus 10 divided by 2. The distance it moves up or down is 2.5. So that'll be 2.5 hours up or down. Alright, so we'll just focus on plotting that part first of all. I'll just type this in to Desmos. I've got a slider there for each of them. So if we just get rid of the C and D values, that's your beginning sine graph, and if we muck around with the A value, you can see it makes it go up and down. 2.5, that there's our amplitude sorted. So A is 2.5. Now we have to move on to finding out what is B, what is our period. So the period for a sine graph, well, normally the period for a sine graph, as you can see, is 2 pi, or one circle. That's where it all comes from. So if I move it, if I make B bigger, as you can see, it squishes up. If I make it smaller, it spreads out. And if I make b equal to 2 pi, it condenses it by 2 pi times. So that means that what was originally 2 pi is condensed 2 pi times. So if the period is 1, we have to compress it by 2 pi times. We want a period of 365 days. So all I have to do is then divide it by 365. Multiply by 2 pi, divide by 365, and that stretches it out so that one revolution of the sine function takes exactly 365. In this case, x is 365 days. So our b value is going to be 2 pi to compress it to 1, divide by 365 to make it a whole year for a cycle. Right, now we'll focus on d. We'll come back to c. We want to shift it up so that the maximum is at 15, the lowest point is at 10. A normal sine graph goes from -1 up to 1, and it rests at 0. Our resting point is going to be 12.5. So that resting point is how much we have to shift the whole graph up by. So d will be 12.5. Right, that leaves us with c. Now we could have written that sine function as sine of bx plus c, but instead we wrote it with sine of b times x plus c, and we put the x plus c in the brackets. Now either of these work just fine, and they both give you a correct answer. The only thing is that the c value will be different in both of them, but you can adjust that. It's all adjustable. We're going to use this top version because when you expand it, b is multiplied by x and c. So we're going to use this one here because this form allows us to take a particular shortcut or follow a particular rule that helps us to remember what to do in any given situation. So here's my original sine function. As you can see, it travels along by pi over 2, and the whole function travels 2 pi before it starts to repeat. So the period is 2 pi, and it travels along pi over 2 before it reaches its maximum point. So if you add pi over 2 in here for c, so I'll just adjust this. So if we make it bigger, it moves it to the left. So if I just shift that along roughly, so you can see what I mean. Now pi over 2, that moves it along so that the maximum happens at 0, which, by the way, is the cosine function. So the relationship between cosine and sine is only a quarter of a circle difference, and that's it. They're the same function apart from that. Right, so our function is going to have a c value, which is going to be equal to minus, and we put the minus in there because a negative value moves it along to the right. And this last bit here is going to be minus the period over 4, because that's how long it takes to move it to the maximum point. And then we have to take away the time to the maximum because that's what we want to shift it to. So that minus period over 4 bit means that we're adjusting for how far it is from the beginning of the sine graph to the maximum point. And then the minus at the start, minus time to maximum, means we'll shift it along so that the maximum point is exactly where we want it. Okay, so December the 21st is 355 days away from the beginning of the year. So our time to maximum is 355 days. Our period is 365 days. So we're going to write that as c equals minus, because we're shifting it along to the right, 355 minus 365 divided by 4. Right, and as you can see, that graph is now shifted along such that the maximum point is right there on day 355, which is the 21st of December. And the minimum's down there sometime in June, halfway along the cycle. So there's our c value. Now we found all 4 values, so that's the end of it. That's all we needed to do to create our function to represent the number of daylight hours in a year on any particular day in Auckland. Maximum 15, minimum 10. And the maximum falls on the 21st of December, the 355th day. Right. So we could use this too, for instance, then answer a question. So when do we have exactly 12 hours of daylight? Well, we could solve this, and we'll do this in another example. But for instance, we'd have to just plot it against y equals 12 and solve for particular values such as that one. And they just go on and on. There's lots of different options next year as well.